Good day to you, my dear friends. It's time to solve some LeetCode problems. Yay! Oi. And as usual, let's start with the problem from the past. Let me find it. Minimum number of swaps to make the string balanced. Well, unfortunately, there are no Ruby solutions for this problem. So, the best I can do is to explain my own solution, I guess. This is my original solution, but what is a problem? We have a string of square brackets. The question is how many swaps we need to turn our string into a balanced string. And a balanced string is a string where you do not have any unclosed brackets, so we need to swap these two, for example, and we're gonna get something like this. But of course we can do this by swapping these two and these two and get something like this. But the question is, our goal is to return the minimum number of swaps necessary. So this is 1, this is 2, of course we need to return 1. And this is my solution. We have a problem here immediately that for some reason I created a hash where I wanted to count the brackets that I encounter, but it turned out that I only use this one. But if we have just one element in our hash, why do we want a hash in the first place? Let's call it just p1 memory 0. So we have 2 pointers. Alright, let's take the same example. We have 2 pointers, p1 and p2 as length minus 1. And memory, p1 memory. And we want to move our pointer 1 to the right and pointer 2 to the left until they cross each other. But we do not do this simultaneously. What is the logic? We check what we encounter. If we encounter this opening bracket, we add it to our memory. So we count how many open brackets we encounter. But this is not an opening bracket, it's a closing one. And what do we do if we have a clause in one bracket? Well, if we already have some opening brackets in our memory, then we understand that we can have a closing bracket too. That's alright. But if we do not have anything in our memory, and this is our case exactly, then we swap. We swap. How do we swap? We check what we have here at our pointer to index. If we have an opening bracket, then we do a swap. If we don't have, then we move our pointer until we encounter an opening bracket. This is not the best example, maybe. They're all bad. Let me create my own example. Say something like 1, 2, 3. Okay, and probably like this, and like this, and like this. Closing. Like this. So we start here, and it's an opening bracket, and we add it to our memory. So our memory is 1, and we move here. It's an opening bracket plus 1. We move here. It's a closing bracket. So we know that with this closing bracket we use one of the opening brackets. So we do -1. Now we have 1 bracket in our memory opening. We move here. It's a closing bracket again. And we have 1 in memory. Now we have 0 brackets that are not closed. And we move again. And it's a closing bracket, but we do not have any opening brackets. Then we check what do we have here. It's a closing bracket. It's bad. We move until we encounter an opening bracket. Here is 1. And then we swap. This one becomes an opening, this one becomes a closing. And if we have an opening bracket, again, we need to increase our memory. Now we have 1. We increase our swaps, it's also 1. And we move our pointer, second pointer here. And this pointer also we move. Why do we need to move this pointer? Because if it is here, actually we do not swap anything. We just change our indexes. We do not touch a string at all. And if you stay here, we again are going to encounter this opening bracket. And we're gonna use it again and again and again, and we're gonna break everything. Because it is not actually swapped with this one. It all happens in our mind, you know. And then we continue, and we do not need to swap anything else. Right? Right. so we need just one swap in this case. That's how it works. Let's check. Probably there is a better way, you know, but solutions section is empty and I do not have time to really investigate like Python solution, trying to understand what's going on there. This is my solution. And you may ask, why don't we just do this while P1 is smaller than, say, something like this, until we reach a middle, because they are not all symmetrical. You see? Nope, it's not gonna work. Maybe you want less or equal. No, again, because it's not necessarily symmetrical. So this is the right approach. And probably there is a better way, because it looks, well, it's not beautiful. It's not beautiful. Okay, let's continue with some problem from the first page. We almost finished this page. And what do I mean when I say first page? Well, not the first page, of course, but the first page of the easy difficulty with maximum acceptance. So the easiest problem in the existence. We almost discussed all of them. I solved all of them a long time ago. Well, not a long time ago, but before I started streaming, I solved most of them, and now we just discuss them and look for the best approaches and so on. So, what do we want to discuss today? This one. Let me reset this problem. We have an array of numbers. We want to return an array of numbers. And for every element in the array, for example, for element 4, we want to return the sum of all the elements to the left of 4, 10, minus the sum of all the elements to the right, 8 and 3. So it's gonna be 10 minus 11, but we need an absolute value, and it's gonna be 1. That's why we have 1 here. And for the first element, we do not have anything to the left, so it's 0, and we have 15 to the right, so it's 15. And there are many ways, of course, to solve this problem. How did I solve it originally? Now let's have a sum of all numbers in our array. Let's call it right sum. Because imagine this 10, 4, 8, 3. 10, 4, 4, yeah. 4, 8, and 3. And we start maybe here. We do not even start yet. But we have 0 to the left, and we have all numbers to the right. So our sum is all of this. What is it? 25? Probably. Yeah. Now, our right sum is the sum, our left sum is 0, and now we want to iterate. Nums each do num. Num num num. So we are here. Our left sum is 0. Our right sum is the sum minus this number that we encountered. So it's 15 now. It's the sum of all these elements. But we do not want to count all of them again. We know that we have 25 at all and minus current number. So and we want to return the array answer. So let's create an array. Answer. What do you want to put here? Well, left sum minus right sum absolute. And now we want to update our left sum. We want to increase it. So this one is 10. We move here. 15 minus 4 is 11. This is our right sum. This is our left sum. So we got 1. See, it works. Of course, it's a little strange that we start from 0 and full sum 25. Let's start with 0. Oh, well, let's check that everything is working, first of all. Great. Let's do nums sum minus nums nah, I like it even less. We definitely have one number. Sorry, I got distracted. Okay, I'm back. So if we go now, well, now we have to start from no, wait a second. Now this do right sum, it's good. Left sum, good. Left sum increased. Well, yeah. Good. Also should work. Oh, wait. And we still need to do this. Oh, yeah, it's a lot worse. Because we need index for this. No, I don't like this at all. I like my first solution better. But is there any other way? Well, yeah, I've seen some people iterating twice. For example, they have an answer array and they do nums each do, let's say, left sum left sum becomes bigger. So now we have, I don't know what, let's check. All the left sums we have in our array now. Now, we iterate again. Let's call it like sum. And let's use this sum again. Although there are two different kinds of sums, and while I is more or equal to 0, or maybe just more, let's see. Answer I is gonna be equal answer I minus sum, and this is also sum, by the way, and this one too. Absolutely. And of course we want to increase our sum, but we can't do this. No, we can do this. Maybe. So in this approach we iterate twice. Oh, it's not S. Great. And when I say that we iterate twice, here I must acknowledge that I also iterate twice in my solution. Because when I count sum, I also iterate. That's why they're about the same, but mine is a little bit shorter. Oh, wait. In solution section, I believe we have a one-liner even, but you know, it counts. It sums all the elements on every step. For example, if we have 10, 4, 8 and 3, when we are here, we sum everything to the left, we sum everything to the left, to the right, we subtract, absolute, then we move here and we do this again. We count everything, not count, sum everything to the left, sum everything to the right, and we do the same for every element. So it's very, very inefficient, but it's a one-liner, you know. And there is one more problem I want to discuss. This one. A somewhat similar problem. So we have a number. We want to count the sum of its digits and a product of its digits. And then we want to calculate the difference between product and sum. What is product? Well, if sum is a sum of every digit, then product is a multiplication of every digit. Of course we want to iterate. And let's say we have a product, and you know we have a sum, of course, and it is equal to 0, and product is going to be equal to 1, because if it is 0 we won't be able to multiply it by anything, you know, so we have to start with 1, and digits each do digit. And product is gonna be multiplied by digit, and sum we're gonna add digit. And that's it. Product minus sum. Great. And if we want a one-liner again, we can make a one-liner. Let's say we want to take all the digits and we want to reduce them using multiplication. Because we do not have a special method for multiplication, and we do the same but sum for sum, and it's not plus, of course, it's minus. Let's check. Also good, but of course we do this n digits 2 times. We can do this in another line, but then it's not a one-liner anymore. But I still think my solution is the best, as I always do. Oh. Great. Now it's time to solve something new. Well, not new. We started this problem yesterday. It's a hard problem, and I want to continue with it. Excuse me. So we have these words, we have these letters, we have a score for each letter, and we want to return the biggest score we can achieve, you know. For example, we can take good or let me check. Dun, 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 dun. Yes, we can take good and dead. This is an example, and we get a score of 23. Or we can take dead and dog, and then we get a score of 21. It's not a very easy problem. And I've been thinking all night and all day, and I think I have an idea. Well, it's a continuation of what I said yesterday, that we definitely need a recursion here. And I entertained an idea of using combination method and to list every possible combination of words and count everything, but it's bad for many reasons. For example, you know, when we use combination, let's say we have an array 1, 2, 3. Four. And we want to return all combinations of two numbers. We're going to return 1, 2, but we also are going to return 2, 1, for example. And in our case, this is the same thing, because order doesn't matter in our case. So we do not want this. And the only alternative is recursion. Oh, it won't be easy. First of all, I'm gonna remove whatever I did here yesterday. Let's see what we have. We have hash scores. In hash scores, we have a score of every letter from A to Z. We have hash letters. This is a counter. How many letters do we have? Like we have 2 A's, 1 C, 3 D. And also I created hash words. What do we have in our hash words? In hash words we have words that can be created from these letters. In like the best case scenario, if we have all of them available, what words can we construct? For example, we can't construct cat because we do not have a letter T. So cat is not gonna be in our hash words. What I want to do, I want to put minus here so that sorted words array is sorted from the most expensive word to the least, or to the word that shouldn't even be here. And that is the second thing that I want to do. I want to iterate again. That would be all sorted words. And let's create okay, let's do this without all. Let's create an array like available words or good words because it's shorter. Good words is an empty array. And if we have a word what the hell? Yeah, that's right. Not sorted words. If hash words word, this is a good word. Let's check our good words. Should be the same but without bloody cat. And you may say, can't we just use our hash words? We have keys and our keys are our words. No, because somewhere in these test cases we have a case when we have the same word twice, like if we had two dads here and we can only have one key, unique key. Keys must be unique. That's why we can't do that. So I iterate again and create another array, but it doesn't matter. They're not big, or they can be big, but in our case 14 is the maximum. Not big. So we have a score for every word, for every good word in our hash words. I want to create another hash. Oi. Yeah, the naming is terrible. So what? Let's create an array here, or not array, hash. We want to count the letters. It's an easier way of doing this. So if score is good, we do this. And also we do word score word is gonna be equal to word characters tally. So for every good word we have a hash with used letters, with letters that we need to create this word. And now we need a recursion, and that's gonna be tricky. So let's start with an index. Wait. Start is 0. And while good words start, it's also let me think. Max is equal to 0. And here max is gonna be equal to max or. I don't know how to call it. Of course it's a bad name. I'm going to create a helper method where we're gonna do all the recursion. So it's gonna be called helper. And that's all we need. By the way, just index well, not just index, but also we want to hash letters, to send hash letters, and we want to increment. So we have an index, we have a hash, and immediately we want to create a copy of this hash and duplicate. That's loud, I'm sorry. Good letters. Well, available letters, but it's too long. It's gonna be hash dupe. What do we do now? We want to make our good words array available everywhere, so that we do not have to send it in this method all the time. We can just send an index and it's gonna be enough. And here we're gonna use good words index. This is our element. Now let's make word score available everywhere, because we want to know what is a cost of good words I, you know. And we have a hash of letters as keys and their frequency count of the letters as values. I don't remember how we iterate hashes, but let's do it like this. So we take our good letters if we have more available letters than we need, we continue. More or equal, we continue. So if we have less, we're gonna return 0 here, because it means that we can't continue. We can't make this word, and we want it to be equal to 0. That's why we return 0. But if this is not a case, then we do that. we have a new starting index and we do pretty much the same thing. What do we want to return here? I'd say, and it's not hash letters, it's good letters now. I'd say we want to return we want hash words. No. Hash words, good words, I. Plus, max. That's what we want to return. I don't know. Probably we're gonna hit something. Let's check. Hit some problem. Hash words, where is it? Line 30. Alright. Hash words and word score. Need to update it everywhere. Good words also. What? Right. Oh, something gonna happen. We hit a time limit or something. Ooh. I was afraid. That was scary. I thought time limit seemed unavoidable. I thought we need more restrictions of some kind when we stop, but no, it's good. Maybe we can add some more restrictions. For example, we can check if our good letters contain only zeros, for example, we do not want to continue at all because we do not have any available letters. But do we want to do this every step? I don't know. I'm very happy. Another hard problem solved. I'm getting better. The only problem is that I have to think for a whole night and then for a whole day to get an idea, a theory. It takes too long. Well, I hope I will get better. But that's it for today. We solved a huge problem. I'm extremely proud. Now it's time for me to go. Yeah. Thank you for being here. I'll see you tomorrow. And goodbye, my dear friends.